In the last lesson, we have already understood that an equation of a plane look like this. R equals to A plus lambda B plus mu C. You want to recall once again that the vector A represents a point on the plane. Like this is a vector, this point A, this is the vector small a, right? And then this one represents the position vector of a generic point. Say this is a generic point on the plane, so the vector R look like this. Okay? And in the last lesson, I stressed that this vector B and C, they are parallel to the plane, but mutually B and C are not parallel to each other. I want to also stress once more that this vector B and C, right? They did not themselves lie on the plane. In case you leave to think from the earlier discussion, think that B and C have to be lying on the plane. This is not a true thing because the vector B and C are just free vector. All that is required is these two vector B and C, right? They just need to be parallel to the vector. So parallel can be on the plane or be above the plane or below the plane. So the vector B and C are just vectors parallel to the plane. So with this understanding, we want to look at the example on page 114. So turn with me to page 114. Page 114. Page 114. I'm going to look at example 1 first. There's an exercise in front, but never mind. I want you to look at example 1 first. In example 1, on page 114, you are asked to find the equation of a plane pi 1 that passes through the point A, and then the plane is parallel to two other vectors. So based on our understanding, this plane pi 1 will therefore have an equation that looks like this. The position vector of a point, in this case, is exactly just A, and then you have lambda of a vector which is parallel to the plane. It could be lying on the plane, doesn't matter, or it could just parallel with you. And then mu of the third vector. And lo and behold, this is the equation of the required line. Simple as that. Right? That's example 1. If now we roll back to look at the exercise above. In the exercise above, there's an exercise above on the same page. It talks about so-called the xy plane, the xz, and then the yz plane. Let's talk about the xy plane first. Xy plane, okay? Xy plane. How do you write down the equation of the xy plane? So again, to write down the equation of plane, I need 3 vectors. 1, 2, and third one. So for the first vector, right, it represents a point on the plane, the position vector of a point on the plane. Can you give me an example of a point on the xy plane? How does the xy plane look like? If this is the x, y, and z axis, this x and this y, okay, this y, and this is z axis. Tell me, where is your xy plane? Your xy plane is actually here. You want to be mindful that although I'm shading the front part, I want you to know that the plane actually extends in all directions horizontally, and it contains both the x and y axis. So for such a plane, like the earlier example 1, to write down the equation of this plane, I need 3 vectors, 1, 2, and 3. For the first vector, what I need is a point on the plane. Can you suggest to me a point that is on the xy plane? Okay, the easiest example that you can think of is actually the origin itself. Right, the origin lies on the xy plane. For this vector, right? For this vector, I have in this case used the origin. Could I use other possibilities? Of course, I could have actually used other points that I can find on the xy plane. Maybe I could even use, instead of 000, I could, if I wish to, any other point on the xy plane. I could even have used, for this, right, I could even use, maybe, I could even use 110. I'm trying to say that actually the first vector, right, it just needs to be a point on the plane. In this case, there are plenty of choices. You could use the origin itself, or you can even use 110. 110 is roughly a vector starting from origin and somewhere like that, right? Next, I need a vector that is parallel to the xy plane. An easy choice of a vector that's parallel to the xy plane, an easy choice would be the vector 1, 0, 0. Where is the vector 1, 0, 0? The vector 1, 0, 0 is somewhere like this. Could I have used other vectors apart from 1, 0, 0? Of course, as long as you can find a vector that is parallel to the xy plane, you can put it in there. So therefore, once again, this vector could have many choices, but you just need one. Then next, I need another vector that's also parallel to the xy plane, but bear in mind it mustn't be parallel to this vector. So for the second vector, for the third vector here, I wouldn't choose 2, 0, 0 because 2, 0, 0 is parallel to this. I must choose something else that is lying on this plane. Sorry, that's parallel to this plane, but it is not parallel to 1, 0, 0. So a good choice, an easy choice could have been just, or to choose, an easy choice would be just 0, 1, 0. And once again, I could have chosen many other possibilities. So there you are. This is the equation of the xy plane. As you're doing this and you're pondering, you realize that actually the equation of plane is not unique. It is possible for me to write down the equation on the same plane with a totally different set of first, second, and third vector. It's pretty alright. They are just equivalent forms for the same plane, right? Now let us quickly write down the next two plane. It also asks for the next one. They ask for the xz plane, xz plane, and then you have the yz plane. Okay, let's follow the same pattern of doing things. I need a first vector, a second vector, and then a third vector. Same thing here, I need a first vector, a second vector, and then a third vector. Of course, I want to highlight to you, usually if all these are from a one same question, right? Typically, we will use a different set of symbol for the second plane and for the third plane. So maybe I should change the symbol to avoid confusion again. I'm just afraid that it may you think that every plane was the same. I could just change to a different set of variable. I could even call them, okay, I could just change the different name. So for the xz plane, again, a point on the xz plane, a convenient choice of a point that's on the xz plane is just 0, 0, 0. What is a vector that's parallel to the xz plane? A convenient choice would be 1, 0, 0, and this would be 0, 0, 1. Likewise, for the yz plane, you can choose 0, 1, 0, and then 0, 0, 1. And there you are, the equation of the three planes that are found on page 114.